Bear Brown, build it with a CLI, then take it apart. 80% of the weights are 0. The benchmark says the model is sparse. The MCU says it runs at exactly the same speed. Sparse on paper, dense in silicon. The problem is that unstructured pruning scatters zeros through the weight matrix, but the embedded kernel, TFLite Micro, CMSESNN, still runs dense GEMM. No skip logic, no sparse path. Storage drops because you can compress a bit field. SRAM and latency do not move at all. Structured pruning removes entire channels, so the matrix shrinks, and every metric drops together. Ask for the experiment. In the terminal, Claude, write prune benchmark.py, dense baseline versus 50% unstructured pruning with scattered zeros and a dense kernel, versus 50% structured pruning with channels removed. Report storage, activation SRAM, and MAC count for each. Read it before trusting it. The benchmark models 3 cases analytically. Unstructured pruning at 50% halves the non-zero weight count for storage, but the convolution kernel still iterates over the full weight matrix. Every multiply, including the zeros. Storage shrinks because a CSR format compresses zeros. SRAM and latency are functions of the kernel shape, not the sparsity pattern. Run it. 3 metric columns. Storage, SRAM, latency. 3 bars each. The dense baseline in slate. Unstructured in crimson. Watch storage drop by half, but the SRAM and latency bars stay exactly as tall as the dense baseline. That is the lie. Structured in ink, all 3 bars drop. Storage, SRAM, and latency all shrink because the kernel itself is smaller. That is the honest picture for today's embedded kernels, but sparse compute exists. It just doesn't ship on most MCUs yet. Iterate, Claude. Add a hypothetical sparse kernel column showing what unstructured pruning would buy if the kernel supported sparse paths. Rerun. A 4th bar appears in each column. Hypothetical sparse dashed border. Storage matches structured. SRAM matches structured. And latency, the punchline, drops to match structured too. The sparse kernel would make unstructured pruning real. The reason you don't use it is that it doesn't ship in TFLite Micro or CMSISNN today. The compression a benchmark rewards and the compression your MCU rewards are different metrics. Unstructured pruning scores well on parameter count and storage. Structured pruning scores well on latency and SRAM, the things embedded inference actually runs against. Optimize for the kernel you ship, not the benchmark you read. Your move. Run prune benchmark.py on your model's actual layer shapes and verify which metrics move. The output beats in this video use illustrative numbers. Swap in a real on-target latency capture once you have the MCU measurement. And if you want the unstructured path to actually work, watch for sparse kernel support in your toolchain. It's coming, just not here yet. Nik Bear Brown, build it with a CLI, then take it apart. At Nik Bear Brown, nikbearbrown.com.